Good morning. In this discussion, we will see how to convert the non-conservative form of energy equation into conservative form of energy equation. Okay, in the previous class, what we have seen, how to convert the non-conservative form of continuity equation and momentum equation into conservative form of continuity equation and momentum equation. Now, in this class, what we will see is the conversion of the non-conservative form of the energy equation into conservation form of energy equation. Now, myself, I am P. Venkata Mahesh, Assistant Professor, Mechanical Engineering Department in Institute of Aeronautical Engineering. Now, see, this is the energy equation that we have derived in the previous classes. What is this energy equation? So, how we derived is, we used infinitesimal fluid element moving with the fluid, okay, with the flow. Okay, the fluid element is moving with the flow. So with that approach, what we did, we derived energy equation, and the energy equation is of this form. Now this is change in energy of the molecule is equal to, now what is this? This is the net heat transferred because of the conduction, and this is the net heat transferred because of the radiation, and this is the work done because of the pressure forces, the work done because of the stresses, and the work done because of the body forces. So the net energy, the rate of change of energy of the fluid molecule is equal to the net heat transferred into the fluid molecule by radiation and conduction, plus the net work done on the fluid element by the pressure forces and stresses, the shear stresses, normal stresses, and the body forces. So this is the equation that we have derived. Now what we have to do, we have to convert the left hand side as a conservative form. So we need a del dot sum term on this left hand side. So how to do that? So we'll take this equation. First, what we'll do, here we have two terms. One is E and V square by 2. So we'll see what is d by dt of V square by 2, what is d by dt of E separately, and then we'll come back to the main equation. Okay. So first we'll see what is V square by 2. We had the momentum equations. So this is the non-conservative form of momentum equation. So when the non-conservative form of momentum equation is taken and multiply this with the x component. This is x momentum equation. We are multiplying with x velocity. If I multiply this with x velocity, what I will get? I will get a u here and u above in front of all the terms. Now what is this? U into du by dt. U into du by dt, if you interpret this, what it will be? It is equal to d by dt of u square by 2. Okay. If you differentiate, you just cross check if you want. So d by dt of u square by 2. What I will get? 2u. What I will get is 2u du by dt by 2. The 2 will get cancelled. I will remain with u into du by dt. So this way, what I am doing is, I have converted this momentum equation in the form of the kinetic energy equation. So this is the kinetic energy equation. Okay. So momentum equation, from momentum equation I got the kinetic energy equation, which is a part of the energy equation. So in energy equation we have internal energy and kinetic energy. So what is the equivalent of internal energy? What is the equivalent of kinetic energy? That we are doing. In the first step, we converted the x momentum equation into the x kinetic energy equation. Now similarly, if I multiply the y momentum equation with v, I will get the kinetic energy equation in y direction. If I multiply this z momentum equation with z direction velocity w, I will get the kinetic energy equation in z direction. So I have the kinetic energy equation in x direction, kinetic energy equation in y direction, kinetic energy equation in z direction. If I add up these three, what I will get? I will get the total kinetic energy equation. So this is a x kinetic energy equation, y kinetic energy equation, z kinetic energy equation. If I add up all these three, what is u square by 2, v square by 2, w square by 2? It is nothing but it is v bar square by 2. It is velocity, so I have just written v bar square. Now, so here the pressure terms I added up here, the stress terms and this body force. If I add up these three, I will get the total body force. I can write it as rho v bar f, like that also I can write. So for the time being I am keeping like this. Now, so here u is have this is the pressure forces, pressure force, the pressure, all the pressure terms are here. Now u I have taken common and I have written like this, v I have taken common in this, I have written like this, w I have taken common and I have written like this, and in this rho is taken common, ufx, vfy and wfz. So what I can write here is I can write v bar dot f. So like that I can write here. So this is about the energy, the term energy. In the energy equation we had internal energy term and kinetic energy term. So what we have got here is the kinetic energy term. If I subtract this kinetic energy from the total energy equation, what I will get is the internal energy term. Okay, so I will do that. So this is the energy equation that we had previously, the internal energy plus kinetic energy. This is the total equation. What we derived just now is the kinetic energy term. So the kinetic energy, we have the pressure, velocity, all these things. Okay, so the pressure term, the shear stress terms and the body force terms, all these terms we have. Now if I subtract this from this equation, if I subtract this equation 2 from equation 1, what I will get? I will get the equation 3, which is the internal energy term. Okay, now we'll see how we have done that. Okay, now this minus this, okay, this minus this means this is heat transferred and this is also heat transfer. There is no heat transfer in this, so I have taken this heat transfer terms. Now coming to this body force term. Okay, here the body force term is there, here the body force term is there, both will get cancelled, so we don't have a body force term here. Now here if you see, we have this dou by dou x of rho into p, sorry, vu into p, dou by dou y of v into p, dou by dou z of w into p. Three terms are there. And here we have, what we have here, u into dou p by dou x, v into dou p by dou y, w into dou p by dou z. So we will see what is the result here. Now if I split this one here, what I will get? Dou by dou x of u p. What I will get here? P into dou u by dou x plus u into dou p by dou x. Okay, so I have simply applied the UV rule. So here I have only this term. Okay, and this is this. So this minus this, so I have eliminated this from this equation, so I have remained with this, it is p into dou u by dou x, p into dou u by dou x. Similarly from this I will get dou v by dou y, from this I will get dou w by dou z. So these are the three terms I am getting for the pressure forces term. Okay, now similarly I can see here I have the shear stress terms, and if I apply UV rule for this and subtract this, what I will get? I will get tau xx into dou u by dou x. So first one, for this minus this one, this minus this one, what I will get, tau xx into dou u by dou x, and this one minus this one minus this, if I write, I will get tau yx into dou u by dou y. Okay, now we'll do one so that it is very clear for you. So same thing I am doing here. I am writing here dou tau, okay, by dou x. This is equal to tau into dou by dou u by dou x plus u into dou tau by dou x. Okay, dou by dou x of tau u we have here, and what I am doing is I have applied UV rule. What I am getting here, tau into dou u by dou x plus u into dou tau by dou x. So this I have u in three places. So tau xx, tau yz, and tau yx and tau zx. See, same for all the three. So if I subtract, I have two terms here, I have one term here. What I am remaining with is this term. Okay, here I have u into tau x. So this is eliminated. So I am getting only this term. So from this minus this, I will get tau xx into dou u by dou x, and this minus this, I will get tau yx into dou u by dou y. If I subtract this from this, what I will get is tau xz into dou u by dou z. Similarly, if I put here v, okay, this is v means I will get y here. Similarly here, this is v. So if it is v, I will get y and v into dou y. So I had here the tau term, u into tau term. So what I will get here is tau into v term. So if I subtract this from this, what I will get is this term. Okay, dou v by dou x, dou v by dou z, dou v by dou y, dou z. Okay, I have three terms here from this. So this one, this one, this one, three terms. From this, if I subtract these three, I will get these three terms. Okay. Similarly, I had here w and so it is tau w by tau z, dou z. Okay. So it is dou w by dou z and it w into dou tau by dou z. So here w into dou tau by dou z is there here. Okay, so if I subtract this one, okay, the dou by dou z. So if I subtract this one from this, I will get this term, and if I subtract this term from this, I will get this term. If I subtract this term and this one, I will get this term. So what we did here, we had the total energy equation, and we from the momentum equation we found the kinetic energy equation. Subtracting the kinetic energy equation from the total energy, what we got is the internal energy equation. Okay, so this internal energy equation we got. Now we have to convert that into the conservative form. We will see now. Now from the from the Newton's law of viscosity, what we had is tau xy equal to tau yx, tau xz equal to tau zx, and tau yz is equal to tau zy. The same thing I have written here also. So in the previous slide, what we had is we had many terms in the equation, and we will see again here. So here the tau yx is there, and here tau xy is there. if I take these two as common, I will get dou u by dou y in plus dou v by dou x and tau zx and tau xz. If these two are equal and I take it common, what I will get? Dou u by dou z plus dou w by dou x. Similarly, I have yz here and zy here. If I take the common, what I will get is dou v by dou z plus dou w by dou y. Like that, I will get a common term. So it will become like this. Now what I have is, I have tau yx. So the tau yx is equal to mu into dou v by dou x plus dou u by dou y. So the same term. So if I substitute this, what happens? This will become square. So this is equal to this. So this will become square. Now similarly here, tau xz is equal to this term. You can see here tau xz is equal to this term, same term, dou u by dou z, dou w by dou x. So I can replace with tau z square. I can put a tau xz square, or I can put a square here. Okay, either I can use this or I can use this. So I can put a square and remove this. Put a square here, I can remove this. Put a square here, I can remove this term from this equation. Now coming to this one, what is there here? I have del dot v, okay, lambda into del dot v bar. What is del dot v bar? Del dot v bar is equal to dou u by dou x plus dou v by dou y plus dou w by dou z. Okay, so this del dot v bar, I had three terms. Now here, in place of tau xx, I have to substitute this. In place of tau xx, I have to substitute all these three terms. So here I have 1, 2, 3. Okay, so 1, 2, 3. So if I substitute this, I have two terms. I will be having two terms here. What are the two terms? One is with del dot v bar. Here all the three cases del dot v bar is same. So what I can write? I can write lambda into del dot v bar as a common, and I can write dou u by dou x plus dou v by dou y plus dou w by dou z. Now what is this? This is again, it is equal to del dot v bar. So I can substitute this del dot v bar and I can put a square here. Okay, either I can put a del dot v bar square, or I can write this dou u by dou x, dou v by dou y plus dou w by dou z square. Like this I can write. Okay, now what is the second term? So this is the first term. We will see the second term. What is the second term here? I have 2 mu. I can take this 2 mu common. Okay, dou u by dou x whole square, this into this, plus dou v by dou y whole square plus dou w by dou z whole square. So this is this into 2 mu. So we had 2 mu here in all the three. So I am getting a 2 mu here. So 2 mu into dou u by dou x whole square, dou v by dou y whole square, dou w by dou z whole square. This is one term we are getting. The other term is, from this what I am getting here is dou u by dou x plus dou v by dou y plus dou w by dou z whole square. I am getting a lambda here. This is one term. This is the other term. So what is the third term I am getting here? I am getting here a square instead of this. Instead of this, I am getting a square. Instead of this, I am getting a square. So if I substitute all these things into this equation, I will get the equation like this. Okay. So what I am getting here, the lambda into dou u by dou x plus dou u by dou y, dou w by dou z whole square. So what we have seen here, and this is nothing but del dot v bar. So del dot v bar square, or this square I can put. So I'm putting here because all are in terms of partial normal form, not in a vector notation, so I kept here normal form. Now here it is dou u by dou x whole square, 2 mu is there and here only 1 mu is there. So if I substitute that, I can take only mu common, so 2 into dou u by dou x whole square, 2 into dou v by dou y whole square, plus 2 into dou w by dou z whole square, plus dou u by dou y plus dou v by dou x whole square, dou u by dou z plus dou w by dou x whole square, dou v by dou z plus dou w by dou y whole square. Like this we will get. Now we will see what to write for this one. What is rho into dE by dt. Now from the substantial derivative, okay, from the substantial derivative, what I have like rho into dE by dt. Okay, so dE by dt, if I put the equivalent of the substantial derivative, what I will get is dou E by dou t plus V bar dot del E. So this is what I will get. Now I had a rho multiplied here, so I have multiply here rho, rho, rho. Like this I am getting from the substantial derivative. This is the same thing what we did in continuity equation also, in the momentum equation also. We are doing the similar things only, so we don't have to worry much. The only procedure, if you understand, it is very easy to remember. Now we have two terms here. This is the first term, this is the second term. Now what is the equivalent of these two terms? Now rho into dou E by dou t, rho into dou E by dou t. So I have a rho and I have a E. So we'll see, you can apply a UV rule for rho and E. So it is dou by dou t of rho E. If I apply UV rule, I will get rho into dou E by dou t plus E into dou rho by dou t. So what I want is rho into dou E by dou t. This is what I want. So I take this one this side. What I will get? Rho into dou E by dou t is equal to dou by dou t of rho E minus E into rho by dou t. Okay. This is the equation I got. Now what is the second term? I have rho V bar E. Three things I have. So use rho V bar and E. You can say, this is one product and this is one. So I have two. With these two, can I write a UV rule? So what is that? Rho V bar into E. Okay, these are the three. Three terms are there, but we are clubbing up rho into V bar and E separate. So if I take a UV rule here, what I will get? E into del dot rho V bar. So that is the first term. Second one is del rho V bar dot del E. So that is the second term. Okay. So first I have to apply this del for E, or I have to apply del for rho V bar. So like that we have to do. If I apply like this, I got this equation. What we need is rho V bar into del dot E. So rho V bar into del dot V. So this is the equation. So for this, what I have to do, I have to take this term this side. So if I take this term this side, what I will get is rho V bar dot del E is equal to del dot rho E V bar minus E into del dot rho V bar. So if I substitute this value and this value here, what I will get is this one. Now here E is there, E is there. I have taken E out. What I am putting is dou rho by dou t plus del dot rho V bar. But from continuity equation, what we have is this one is equal to 0. Okay, the continuity, what continuity equation says? Dou rho by dou t plus del dot rho V bar is equal to 0. So if I substitute that one here, what I will get is equal to rho E dou by dou t of rho E plus del dot rho E V bar. So this is the term I am getting. So if I substitute that one there, I will get the conservative form. So here what I have, the for E we have found out, what is that we have found out for dou E by dou T, how to split that, what we got here, you can see here clearly. Okay, what we got here, dou rho into dou E by dou T is equal to dou by dou T of rho E plus del dot rho E V bar. So this equation we have to remember. So if I take this one there, what I will get, what we got previously, dE by dt is equal to d by dt of rho E plus del dot rho E V bar. So this is the equation that we got. Now if I want this dou V by dou T, okay, we had here dou V square by dou T, this one. So if I want to convert this, what I have to write here into this form. Okay, what I am writing here, I am writing this equivalent of this dou by dou T of V square here. So what I have to write here, I can write dou by dou T of rho V square by 2. Okay, here I have rho plus del dot rho V square by 2 V bar. Okay, similarly. So similarly I am writing, instead of E I am putting here V square by 2. If I put V square by 2, it will become like this. If I add up these two, I will get this equation. What is this? Dou rho into dou d by dt of E plus V square by 2. So this is equal to dou by dou T. Dou by dou T is common. So here this is dou by dou T. Here it is total derivative. I am making it into partial derivative. So it is dou by dou T is common. Dou by dou T. Here rho E is there. Here rho E plus rho V square by 2. Rho V square by 2. This is one term. The second term is del dot. Del dot here. Del dot into rho E V bar. Rho E V bar plus rho V square by 2 V bar. So E plus V square by 2 I am taking common. Rho E plus V square by 2 into V bar. So this is what we are doing. Now if I put this one on the left hand side, then this will become the conservation form of energy equation. So what we did here, we found what is the equivalent of the kinetic energy, what is the equivalent of the internal energy, okay, rate of change of or the substantial derivative of internal energy, the substantial derivative of the kinetic energy. Okay, why we did that is just to say that this can be done separately. Okay, now if I done this one, if I can split this one for kinetic energy and internal energy separately, okay, and this the left hand side also I can make it separate, E and V bar separately. I can make the total derivative into the partial derivative terms. Okay, so by doing that, what I can do, I can simply add up and say that this is the final conservation form of energy equation. Okay, so what we did, we have splitted the total energy equation into the kinetic energy equation and the internal energy equation. We found the conservation form for the kinetic energy term and the total internal energy term. We added up those two and finally we got the conservation form of equation for the total energy equation. Okay, So this is about the conversion of the non-conservation form of energy equation to conservation form of energy equation. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.